From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
Directed energy technology perhaps first entered the public consciousness in the 1980s through the controversial Strategic Defense Initiative, or as it's more commonly known, the Star Wars program. The program began in '84, and by '87, the American Physical Society came to the conclusion that the technologies were decades away from readiness, and the budget was cut. But directed energy research went on. Over the past few years, the military has been testing various directed energy systems and their ability to defeat threats like missiles and drones. While we haven't yet reached a program of record, the technology is coming quite close and has re-entered the public consciousness. While high-energy laser weapons might be the first thing that we think of, directed energy systems are much more complex. Beyond lasers or microwaves, there are tracking and imaging systems, optics, computing, and artificial intelligence that all have to work together to send a beam of light to its intended target. Building these systems is a collaborative and multidisciplinary effort. Today's guest is one of the top minds leading those efforts. Professor Martin Richardson is the director of the University of Central Florida's Center for Directed Energy, one of the nation's top labs focused on directed energy research. In today's conversation, we'll discuss how the technology has progressed, its multidisciplinary nature, and potential applications beyond the battlefield, and even beyond the planet Earth. Up next, our conversation with Martin Richardson. Directed energy technology has been around for quite a while now, but only recently does it seem to be gaining traction when it comes to practical military applications. I wondered if you could give us just sort of a quick history of the technology, maybe just highlighting a few major milestones in terms of research breakthroughs and initiatives from the government.
Well, directed energy is not really new. History tells us that, in fact, perhaps the first application of directed energy was back in 2012 BC, when Archimedes arranged to use big mirrors to focus sunlight on the approaching Roman ships that were approaching Syracuse in Greece, and supposedly destroyed part of that fleet. Of course, in nearer term times, directed energy specifically, when we talk about directed energy, we really are talking about directed electromagnetic energy. And electromagnetic energy, of course, spreads from the radio frequency band through microwaves, through terahertz radiation, visible radiation, even into the X-ray radiations. This is all electromagnetic radiation. And more specifically, in recent times, directed energy weapons has really focused in the last 40 years on laser directed energy weapons. Though nowadays, we must also include high-power microwaves as also in that class. Some of you will recall that back in the 1970s, 1980s, there was a large directed energy weapon program called the Airborne Laser Lab, or the ABAL or the ABL, very strongly focused program to locate an extremely powerful laser system on an aircraft, initially a K-135, and then the ABL system was mounted on a 747 to counter the threat from ballistic missiles.
Right.
intercontinental ballistic missiles, that is. And this was part of the old SDI, or Star Wars program.
Right.
It was successfully demonstrated as a weapon. It shot down missiles in several important tests back in 2010. But subsequently, the program was cancelled at about that time, 2010, 2011. And in terms of laser-based directed energy weapons, didn't really start to appear again, sort of in the national consciousness, until a decade later or so. And though, in fact, Congress set up a joint high-energy laser joint technology office back in 2000, and that office has started to promote the development of laser-based, particularly initially laser-based weapon systems that could counter the new threats of the age, which now, as we know, are swarms of small drones, missiles, mortars, even in the future, hypersonic missiles. So there's a whole range of new threats, and these threats create really new challenges in the development of laser and hypersonic based, sorry, not hypersonic, high power microwave based weapon systems.
So I remember seeing an article a while back. I think it was sometime the last year. They'd interviewed a bunch of folks in the military who had worked with these systems, and by that I just mean that they were operating them and sort of testing them, not being involved in the development. But it seemed like there were a lot of complaints about these systems and their usability. Um, and so I guess my question is, what are some of the things that we're learning, since they've been tested and, they're being used now in the field?
Well, I think you must recognize this is this is a fundamentally different type of weapons system, particularly in terms of being a defensive weapon system. And I am sure, like all new systems that are utilized in almost any environment, there are lots of problems.
Yeah.
It, nonetheless, I think your comment relates perhaps to some time in earlier from what I'm hearing, and I want to state pretty clearly I'm an academic working in this field. I personally am not directly involved in the development of these systems. Rather, I'm an academic that is leading one of the most well-known university research teams in this field in this country. And of course, our focus is to focus on the fundamental science, to open up the knowledge base in those fundamental sciences. I emphasize here, and I hope we do have an opportunity to discuss the breadth of the science and technologies that are involved in this work.
Sure.
And in addition to the science itself, of course, to work on specific technologies that advance the field. And those technologies are in a large number of areas. They're not just associated with lasers or hypermicrowaves, but with systems, imaging systems, ultra-fast tracking systems, advanced computer systems involving AI and other data analyzing technologies. Yeah, so that's where I see my principal role as an academic, but also I think that rightly so. This is where universities play a very important role in contributing to the depth and also the robustness of these new technologies. And the feedback I've received very strongly indicates that this is a very promising technology um, from the viewpoint of the warfighters themselves. Not only do the warfighters learn how to use these systems, but in essence, they take their experiences to define how they can be used. Because these systems will not be used in isolation. They'll be used in conjunction with other more um, more more developed systems that are already on board in terms of a kill chain, if you like. Um, so the feedback has been very, very positive at pretty much at all levels. At the command level, one of the great supposed advantages of these systems is that the quote the cost per shot extremely low. Some people have said, cents on the less than $1 per shot, however you want to measure it. But suffice it to say, when you switch on a laser system and switch it off, it's energy you're transmitting, and that's pretty much the sole cost of the silo. Not so much the silo of the shot itself, um, as compared to, for instance, utilizing a missile of some form to bring down either a missile or the biggest challenge these days are, low cost, commercially developed or variants of commercial systems of uh, um, low velocity drones that can be in swarms, where the drones themselves are $10,000 or less in cost, right? And if you think about using, for instance, a Sidewinder missile to take out one drone, Sidewinder costs now are typically $400,000 a piece, maybe more. So it's not only cost, it's also the extent of the magazine, right? Particularly magazines on marine platforms, which are limited in size, and the cost and time of renewing the magazine or replacing the magazine limits the use of these weapon system as compared to a directed energy weapon system, which would, in essence, have quote infinite magazine.
You touched on the multidisciplinary nature of this type of project. Where there's the targeting systems, there's the imaging, the tracking, the computer aspect of it. Um, I'm wondering sort of where the bottlenecks are, and I say bottlenecks because I'm assuming that there's multiple areas I would expect that we'd want to be improving on. And I'm wondering what sort of the biggest ones are that we're working on right now.
Um, you might not be surprised to expect that, in fact, the focus of those developments can change over time. Yes, initially, the biggest challenge was developing laser systems that are powerful enough to be effective. There's been a lot of exciting progress in that area in the last decade in particular, initiated but by the development of high-powered laser diodes and laser diode arrays back in the 1990s, which can now be incorporated into solid-state laser systems that provide, in essence, efficient excitation of those laser systems. And so, as I mentioned, there's been a lot of progress now in developing laser systems up to the power levels of almost approaching the power levels that were used initially in those airborne laser labs. That's not the only challenge. The optics associated or needed to put into beam directors, for instance, the tolerance of those optics to these high powers, any nonlinearities that may occur in the optics themselves due to them heating up, for instance, in terms of their the fact that they're transmitting laser power. We are learning that when we are using these propagating high power lasers beams in the atmosphere from ground level, that the atmosphere is in many respects not a clear day type of atmosphere, but rather a mixed soup of turbulence and winds, of particles, aerosol particles in the atmosphere, let alone clouds and raindrops and things. And these could be challenges, or at least they offer us a new challenges in terms of understanding how laser light can be transmitted through these atmospheres. Yeah, you mentioned targeting and tracking. Obviously, being able to not just to illuminate, but also to identify and to track moving vehicles. These need not be. We've focused on drones and the like, but they could well be vehicles. They could well be small boats in the ocean. So yes, there's a multitude of potential threats that can be countered with directed energy, and that's the part of the excitement over the advances that have been made in directed energy in the directed energy community in the last, as I mentioned, the last decade or more.
Today's episode is brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical and infrared imaging knowledge and manufacturing expertise to be your optics and thermal imaging solutions partner every step of the way. Visit lightpath.com to learn more.
Now, I wonder what are some of the near-term goals to sort of push this technology further? Are there any like specific like targets or milestones or energy levels or?
If we talk about threats for the moment, threats of other technologies, then there's a number of different threats coming in different directions. We've mentioned drones, specifically now swarms of drones, autonomous swarms of drones, where basically a cloud of drones becomes the threat. Do we recall the? I think it was the final day of the Olympics in Tokyo, when there was a beautiful display of close to 1,000 drones in the air performing. Uh, uh, so imagine that as being a threat rather than being just an attraction at an event like the Olympic Games.
Yeah, very very different attitude towards them. Yeah.
One then might just imagine the scenario beyond that, and the sense now where you imagine maybe a scenario where not only are there maybe swarms or individual ones, and perhaps having different functions, imaging, carrying kinetics, uh, sensing, but there's also an environment where maybe we have drones in the same environment. So then the issue becomes not only dealing with some of these issues we've touched on, but also distinguishing between friend or foe, and being
Right.
able to discriminate in targeting.
Sure.
And I briefly mentioned before that most of the military experts in this field see this technology as being an additive technology to the ones that they already have. So, in any environment, directed energy will be, in essence, another quiver, another arrow in the quiver of arrows that a commander has towards addressing a threat that he or she sees. and making the appropriate decisions accordingly. We are fortunate in our military commanders out there in the field. They have the experience to decide what countermeasures can be used to counter specific threats that they see on the battlefield. Of course, those threats can change, of course, from one day to another. It's an exciting domain of science and technology, but it doesn't sort of fall simply into one bracket or another of education. It's not chemistry, or rather, there is some chemistry in it. It's not just physics in terms of the physics of how laser systems work and new laser systems, or the physics of how to new systems, designs and systems that generate high power microwaves. It's also the physics of how these microwaves and these laser beams interact with materials and targets and shapes and material combinations, and active systems that are the object of all this work, right? And these provide a lot of opportunities for the next generation of scientists and scientists, engineers, technologists, atmospheric scientists, and in a whole host of fields. Communications technologies. I have difficulty sort of listing all of them here, but I think the listeners would can clearly get sort of an understanding of how broad this new capability of projecting high powers, and they need not necessarily be high continuous powers. They could be high pulse powers or bursts of pulses, bullets of pulses. We talk about light bullets now. Um, uh, Light bullets that propagate through the atmosphere, where we utilize the nonlinearities in the properties of the atmosphere to actually change uh, the characteristics of the light itself, where we utilize the properties of light, its spectrum, its phase, for those of the or phase distribution, uh, where you can, in essence, change the shape of a beam as it goes from one place to another. Um, you can change its as a pulse. You can change its pulse mode, its pulse shape, its color, the color of the light. Uh, there are many very exciting outcomes of applying advanced optics and advanced optical theories to propagating laser light, particularly pulse laser light.
I'd like to ask about that. You mentioned like the different properties, the phase and the phase distribution, um, and pulsed versus continuous wave. What are the benefits to sort of making those changes, and how are those changes, I guess, informed? How do you make those decisions on what to change?
One of our strengths are that we know how to build laser systems that have well characterized outputs, if you like. One particular aspect is to make laser beams, particularly laser beams that come from, say, high power fiber lasers, where as the laser light leaves the laser, the phase distribution is extremely well known, and the simpler it is, the better. When it propagates in essence as a classical beam, it would propagate simply as a diverging um, beam with a uniform beam shape as it propagates. Well, we can modify, if we then deliberately modify the phase distribution as the beam leaves the laser, and we can. even with high power laser beams, then the beams themselves, what we say in the far field, in other words, focused way out at a distance, can, in essence, the single beam can be manipulated to create arrays of separate beams, even structured arrays of those separate beams. Now, those separate beams can, under certain circumstances, be such that they can act, say, as an atmospheric lens, a transient atmospheric lens, if it's for using pulsed laser radiation, but a transient lens that could be, or other optical component, in the microwave region. We have this, one of the beauties of being able to use electromagnetic radiation to address many of these exciting challenges of the future, just not defense applications. But by using our expanding knowledge of how we can manipulate light, and when I say light, I mean electromagnetic radiation, because we can manipulate microwaves and even radio frequencies and X-rays in many of the same ways to accomplish new modalities of directed energy, if you like to call it that way. These are opening up applications in many different fields.
One other thing I wanted to ask you about, before you were mentioning, sort of some of the challenges with the atmosphere and with weather, aerosols and water droplets and things like that. How are we addressing those sorts of challenges?
I like to tell my students here the story that goes that when there are various forms of this story, but one of them goes that is when Einstein was about to meet his maker, then he envisaged that he'd be asked two questions. Dr. Einstein, explain to me what quantum mechanics is and quantum theory. Well, as nearly all of us know, Einstein didn't believe in quantum physics, right? So he said for me that is an easy question to answer. But the second question that he envisaged his maker asking him would be, well, now, Dr. Einstein, explain to me what turbulence is. And we are still having a lot of difficulty. I wouldn't exactly say understanding turbulence, but certainly characterizing it and certainly being able to model turbulence in different media accurately. And in what we've been talking about today, that is the propagation of laser light through the atmosphere, specifically from ground level or at ground level, then there are many factors that actually create turbulence. In this sense, we think largely of eddies or winds of either small scale or large scale, produced by different effects.
Right.
A tree in the sunlight is a source of turbulence adjacent to that tree, and it's different, of course, at nighttime. The very ground itself and the temperature distribution across the ground has an impact on air turbulence several meters or so, tens of meters so above the ground. Learning all about propagating through this and turbulence, or these air turbulence is really wind, if you like, is really a slight change in the density of the air, right?
Right.
It causes us slight change in density of the air, and that change in density manifests itself as a change in refractive index. And as you know, all lenses depend upon refractive index, so that will change the propagation of a light beam, be it also a light beam high power or low power.
Yeah.
Absorption of the atmosphere. The atmosphere is not totally transparent. We know that it consists of gases, and the gases have absorption bands at different wavelengths. Some of those wavelengths correspond to or overlap the wavelengths of the laser systems we want to propagate through the atmosphere. If now you propagate light through an atmosphere and there's some level of absorption, the beam itself will tend to heat the atmosphere. That heating changes locally. That heating will, in essence, create a thermally created lens in the atmosphere, which then changes the the, the the transmission of the beam itself. Lots of
Right.
interesting and challenging topics now are being investigated, and I have to say I'm happy to say that there's some super bright graduate students I have the good fortune to work with are now addressing some of these challenges.
How do you even go about that? I mean, there's just such an incredible number of variables, which you've described with the turbulence, the wind, the heat. It just seems so difficult to kind of wrap your head around. I was wondering if you might be able to talk a little bit about some of the approaches.
Well, this propagation of light through the atmosphere is, in some respects, not a new topic.
Right.
People have been studying this for 50 years or more. It really took off, of course, when we had the capability to propagate beams across distances of kilometers, even tens of kilometers. Technologies like those we've discussed already, but also optical sensing at long distances and the like. So it, we know the problem is there. We've become much more sophisticated now in characterizing the atmosphere itself. So we use many optical and particle measuring instrumentation to characterize the atmosphere along the potential path of a laser beam. We use lots of different optical techniques to relate those measurements to the basic characteristics of the atmosphere itself. You mentioned earlier aerosols. Well, aerosols can affect propagating laser beams in particular by obviously obscuring the laser beam or partially obscuring the laser beam. But we can use the laser beams themselves to manipulate the aerosols, right? If the aerosols themselves absorb, which normally they do, then they will vaporize. Of course, the vapor will still be there and still absorbing, but in a different way, and will have a different impact on the laser beam themselves. In my research group at UCF, we've done a lot of scientific studies, if you like, of laser beams that focus on individual aerosols, well-characterized aerosols, and we can examine how the aerosol, how it vaporizes in the states of matter it goes through as it vaporizes, even to the point of where laser beams can ionize the aerosol as it disintegrates. Yeah, so there's a lot of really nice fundamental science that some of our students get to work on. I must also add that, in fact, there are a lot of applications of laser irradiation of aerosols. I might just mention one, and that is in the computer chip industry. As everyone knows, advanced computer chips are made through lithography, and the shorter the wavelength that you use in those lithographic systems, the smaller the feature sizes you can print. And we're down to, in the latest computer chip manufacturer now, we're printing the computer chip industry is now printing devices with feature sizes down to just a few nanometers in size.
Right.
So what light sources can you use actually that still that can print these very small features? Well, you need to use light of extremely short wavelength. The wavelength has to be characteristic of the feature size almost. A research program that we had and now is widely being adopted in industry uses aerosols of small metals or metal-doped aerosols as light sources for soft X-ray radiation sources that are now being used to print computer chips.
Excellent.
So, yet alone, this is another form of directed energy. I might, in passing, since part of my life experience in lasers and the application of lasers, where I spent a couple of decades working on the program of what's now called laser fusion, the use of lasers to illuminate, again, aerosol type targets that contain fusionable, thermonuclear fusionable material, in essence to create micro suns in the here on Earth. A lot of exciting results recently have been reported from the Lawrence Livermore laboratories in California, where there's a very large laser system. Many people in the optics field know the so-called National Ignition Facility, NIF facility, where in just the last 2 to 3 years, the team at Livermore has been able to demonstrate energy gain in thermonuclear fusion for the first time. It's a consequence of directed energy. The laser beams, in this case from a massive multi-billion-dollar laser system that emits up to nearly 200 laser beams all at one time, laser pulses all at one time, and focuses them onto microscopic targets that then result in the implosion of little aerosols. It's all directed energy.
Yeah.
No? And so this very attractive field for the next generation of scientists and engineers is obviously multidisciplinary engineering. It's a very exciting field for them to think about for their careers.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.